So the topic of today's lecture will be Fourier analysis and quantum mechanics. However, before we start with Fourier analysis, it's useful for us to motivate why we need Fourier analysis. So quantum mechanics deals with wave phenomena related to the matter waves that was proposed by de Broglie. So the mathematics of wave phenomena is best described using Fourier analysis. However, before we discuss Fourier analysis, it's a good idea for us to do a bit of warm-up and review Fourier series. By the way, I'm assuming that most of you have seen some Fourier analysis and some Fourier series. So my review of Fourier series and Fourier analysis is not going to be exhaustive. It'll be more of a bird's eye view. Okay, so let's start. And let's start with Fourier series. So what is Fourier series? So consider a real function, and we shall be generalizing to complex function readily. Suppose we have a real function phi of x that is, actually I'm just going to call my real function not phi of x, but so consider a real function psi of x, and we'll be generalizing to complex functions readily, is defined in some interval on the real line between minus L by 2 to plus L by 2. So here we have the function, and here this is a segment of the real line from minus L by 2 to plus L by 2, and our function looks something like this. Now suppose we extend this function onto the whole real line by translating this function by L, an integer multiple of L. What it means is that we are taking this function, let me just, do this. So we're taking this function, and then what we're doing is that we are making copies of it, and then we're translating it along the real line. And we are translating it along the real line, but in multiples of L. So we can have more, we can have stuff going around there, so on and so forth. And let me just erase these guys. So, okay. So let's call this extended function, phi of x. So phi of x, when we restrict phi of x to the segment from minus L by 2 to plus L by 2, gives me the original function psi of x. So according to the theory of Fourier series, we can express the function, the extended function, phi of x, which, as you can see now, is a periodic function whose period is L. It can be expressed as a linear combination of sines and cosines. So it's going to have a part. It may have a part which is a constant part, and then it'll be given by an infinite sum, and there'll be an even part which is given by the cosine. So it'll be 2 pi n x by L, and then there would be a part which would be the sine part, which would be the antisymmetric part, So this is the famous Fourier series. The coefficients an and bn, so they are called the Fourier coefficients. And of course, these coefficients are the ones which contain all the information about this function, because these guys are just well-known functions. So the size of the value of these things determine how much of a particular cosine or a sine contributes to this to describing this function. So we can use some nice properties of sine and cosine function to express the Fourier coefficients in terms of the function phi. So the nice properties there of the sine and cosine function, they're known as orthonormality or orthogonality properties. Let me write that down. And these properties are very easy to show. The first one would be 2 by L if we integrate from minus L by 2 to plus L by 2 of the sine, where 2 pi m of x by L, m is an integer, times cosine of 2 pi n of x by L, n is another integer which may or may not be equal to m. If we do this integral, then this is 0. So this is orthogonality. So we also have to specify what happens when we integrate two sine functions and two cosine functions. So let's start with the cosine. So if we do a similar integral, so cosine 2 pi m of x by L and cosine of 2 pi n of x by L d of x, then this will be 0 unless m and n are equal. And this is quite easy to show. You can of course do this separately, do this integral separately, but I will show a nifty way of doing all of them at the same time after this. So, and then we need to also specify what happens when we integrate two sine functions. And you've guessed it, probably. Sines and cosines are essentially brothers. They're essentially the same thing, so this will be also have the same result. So these are the orthonormality or orthogonality conditions. So we can use these and we can multiply our Fourier series with a specific cosine or sine and then integrate from minus L to plus L to extract these coefficients. And if you do that, then the coefficients should be given by the an coefficients are given by 2 by L. There's an integral from minus L by 2 to plus L by 2. The function phi of x, and then we have cosine of 2n pi of x by L and d of x, and the b coefficients are given by 2 by L minus L by 2 to plus L by 2 phi of x, and then this would be given by the multiplying it with sine of 2 pi n of x by L over dx. Right. So there's a more succinct way of expressing the Fourier series, and that is by using complex numbers. So we use Euler's formula to combine the cosine and sine into one exponential. You all know Euler's formula, of course. It's given by e to the I. Theta is cosine of theta plus I sine of theta. So if you use Euler's formula, then the Fourier series can be expressed as summation. Now the sum goes from minus infinity to plus infinity. We've got some new coefficients we're going to call Cn, and then there'll be an exponential I, there'll be 2 pi, and there'll be an n x over L. So these coefficients Cn are related to the other coefficients A and B in the following way, where Cn is going to be, if n is positive, then Cn is going to be half of an minus I bn. And it's actually equal to half of a 0 when n is 0, and it's going to be equal to half of a minus n plus I b minus n when n is less than 0. So these are the coefficients for the Fourier series in its complex form. And we can also invert this relationship, and I'll give you the formula for inverting it shortly, but you can invert it to express the coefficients in terms of the Fourier series itself, the function itself, and the function it'll be given by minus L by 2 to plus L by 2, and there is the function phi of x and e to the power minus I 2 pi nx over L dx. So to get this from this guy, we need some sort of orthogonality conditions for the exponentials, and the orthogonality condition for the exponential is given by a very simple formula, 1 over L minus L by 2 to plus L by 2 e to the power 2 pi I m x over L e to the power minus 2 pi I n x over L dx, and that is going to be equal to delta mn. Now it's worth just spending a minute on this orthogonality relationship and see why it makes sense. So the idea is that when m is equal to n, the integral is just 1. The integrand is just 1, and we're integrating it from minus L by 2 to plus L by 2. So the integral just gives me 1 because there's a 1 over L here. And that's how we get 1 over here when m is equals to n. But when m is not equals to n, what we get here is a phase. And what we're doing here is that we're integrating the phase over the whole circle. So essentially, we are going to get 0 because all the phases will cancel each other out. So when m is not equals to n, this thing goes to 0. Now, if I use Euler's formula, which is given here, if I use Euler's formula and express this, then the real part and the imaginary part should give me these three relationships. So you might wonder, well, the imaginary part and the real part are two equations. How can I get three relationships from them? Well, I think you can figure that out. All right, so let's move on to another question, which is how well does the Fourier series approximate the function phi of x? So, how well does the Fourier series approximate phi of x. So to do this, let's introduce a kind of a measure. Let's first introduce a partial sum. So let's call Sn is a series, and it's a series which goes from minus n to plus n, and there are some coefficients which we haven't decided what they're going to be. Let's call them dn, and then there are the usual Fourier functions, which are 2 pi I n x over L. So, I just want to point out this dn's have nothing to do with the Fourier coefficient cn's. So this is some arbitrary series, and it's kind of a partial sum, so that's why I'm calling it S and n. So let's ask, how well does this partial sum, this series, approximate the function phi of x? So let's introduce a measure for error. So let's consider epsilon n, and epsilon n will be a measure of error in the sense of least squares. So it's going to be an integral from minus L by 2 to plus by L, and then we are going to take the function phi of x and take the difference with S of n and take the modulus squared. So this is why it's kind of a least squared error function. So now we can do is that we can just like expand this out. This is square, so we can expand this out. So if you expand this out, the first term is going to be this guy, and then we'll have some terms which will be like cross terms. So there'll be phi of Sn star d of x, and then there'll be terms which is like phi star of Sn d of x, and there will be a term which will be Sn mod squared of d of x. So then what we can do is that we can evaluate, we can look at these guys. There's given in terms of a series given here, and they have some exponential factor, and phi also has some exponential factor. So we can use our orthogonality relationships to simplify these three terms, and then we can rewrite this as so the first term, we don't simplify it because we don't need to. We're just going to compare with that. And then in the second term, we are going to get some series. And one thing we're going to get is we're going to get a factor of L outside. And then we are going to get dn star Cn plus dn Cn star, and then we are going to get minus dn star dn. So we are getting this guy from here and these two guys from these two terms. All right, so now what we can do is that we can rewrite this in a way. So we can subtract a term. So let's subtract a term. So we subtract n, the mod squared of the first n terms of the Fourier series times L. So we have to add this guy. Now if I add this guy to this thing, then I can rewrite, there are four terms then I can rewrite those guys as a complete square. I made a mistake here. This should not be, this should be from minus, should be from minus big N to plus big N. All right, so here, we have a factor of L, and then we have dn minus cn mod squared. All right. So, so this is my error function. Now, look at this function. We have, we have the first term, which is just our original function. This is determined, and this term, cn is also determined by the choice of this function and the integer n. But this depends on dn, our choice of dn. So we can ask, how can we minimize these error functions? That is, how can we choose these coefficients dn in our series Sn such that this error function is minimized? So we can see that this error function is minimized if the dn is equal to cn, because this is a squared term. This goes to 0, and the other terms remain unchanged. So if we choose dn to be equal to cn, we see that en is minimized in the sense of the least square. So this means that if we approximate our function phi of x, by a truncated Fourier series, up to n terms, that series is going to be the best series that approximates this thing. That's going to be the best approximation in the sense of least squares. And so further, it can be shown that this error goes to 0 as the number of terms that we keep in this approximation, goes to infinity. And therefore, in that limit, what happens is this error goes to 0. Of course, we are choosing dn to be cn, so this is also 0. So in that limit, what we get is 1 over L, the integral from minus L by 2 to plus L by 2, then phi squared d of x is equal to the summation where n goes from minus infinity to plus infinity, then we have cn squared. So this is a very important result, and this is known as Parseval's formula. So what is the interpretation of Parseval's formula? What it's saying is that the left-hand side, which is a measure of how, what the function, what the total area of the function is, so to speak, is given by these coefficients. So we can imagine these coefficients as being some, real numbers. They don't have to be real, but, let's just assume for the sake of, argument that they're real. Then, they are going to be, actually, they don't have to be real. Sorry. Then basically these are the cn squareds, and this is on the x-axis we have the integer n, and here I have 0, 1, 2, 3, 4, 5, ... Here minus 1, minus 2, minus 3, ... And these are essentially given by these numbers, give you some sort of skyscrapers. And yeah. And this area, under these skyscrapers, if you add them up, that's basically what this thing is. So this is the interpretation of Parseval's formula. Anyway, it's a good place for us to take a break. In the next video, we will discuss how we can get from the Fourier series to the Fourier integral.